Professor Enrico Scalas is a professor of probability and mathematical statistics at the Department of Statistical Science of Sapienza, University of Rome. He is a co-author of more than 140 publications, including 2 monographs and an edited book. If you like the bibliography, you will be delighted to know that his works have received more than 11,000 citations, and his H index is 43, according to Google Scholar. Otherwise, you may be just interested in the fact that his research concerns the foundations of economics, finance, and statistical physics, and for this reason, he became the probabilist working on various stochastic process, often with the fractional flavor. Thank you very much, Professor, for joining us. You may please begin the talk.
Thank you very much. Thank you very much for organizing this impressive series of seminars. And just now, I am also publicly apologizing for not being able to attend all of them. But on Friday afternoons, I was teaching, so I am catching up using the very useful YouTube recording, and seen already 4 seminars of this series, 2 of them on YouTube, and 2 I've been able to attend in person in the last 2 weeks. So thank you very much to all of you being here, to the organizers once more. And let me start with this talk, which has a tutorial flavor, as we agreed at the beginning when we were discussing with the organizers. But let's say that the first part also contains some new results, even if they are sort of elementary results, as you will see. But then the second part is taken from a paper that was published in 2008, and that I am going to describe in a little bit of detail. And at a certain point, we will also see how to simulate continuous time random walk using Monte Carlo simulations. Possibly trivial for many of you, but you never know, let's say. The presentation is divided, in fact, into 3 parts. Part 1 on some alternative history about these kind of problems. Then the second part is on the 2008 paper. And the third part, the second part is on the definition of continuous time random walk, and the third part is on the 2008 paper in more details. But you will see that they are all connected, and hopefully the main message will be taken home. So the first thing I want to underline here is that the work I am presenting has been performed with Nikos Georgiou at the University of Sussex, Guido Germano, at the time he was at Marburg, but now he is at UCL, Rudolf Gorenflot, who unfortunately died some years ago, Daniel Fulger, who was in Marburg as a PhD student of Guido Germano and myself, Istvan Zoltan Kish at the University of Sussex, Francesco Mainardi at the University of Bologna, and Marco Roberto at the University of Genoa. So first part is, as I told you, about an alternative history of the relationship between stochastic processes and fractional differential equations, or pseudo-differential equations of fractional type. And it is a part of the history that has not been considered by Yuri Luchko when he presented in this series, because it concerns mainly physics and not mathematics. And the physicists became interested in non-Markovian processes quite early, but I can trace the evolution to at least Los Alamos, and the work done also by Montel, Weiss, Harvey Sher, etc. And more in the summary and some details on physics approach to non-Markovian processes can be found in these two papers, a paper by Henge and Thomas from 1977 and another paper by Henge in 1978. So we are talking, of course, Luchko started with Abel. I am starting from the mid of the 20th century and highlighting some results from the 70s. I would like also to stress that in 2000, with Mainardi, Gorenflot, and Roberto, we derived I call it Cauchy-like equation for continuous time random walks. I will present this equation later. It is equation 2.6 in the paper Fractional Calculus and Continuous Time Finance 2, the waiting time distribution. This paper was not quoted in Cauchy-based paper from 2011, but this is understandable because probably he was not aware at all of this result, as it always happens when you have cross-disciplinary research, because this was published in a physics journal, and moreover, in the title there is nothing related probably to the interests of Cauchy, because it's referring to continuous time finance somehow. And therefore, I must confess that for this reason, because of course, when we are quoted, we immediately receive nowadays notifications that the paper is quoting our work. But if we are not quoted, we don't know maybe of important works. And in the case of the paper by Cauchy, I learned of its existence many years later, when I was in, I think, 2018 in Providence at a conference at ICERM, and thanks to the presentation by Yuri Luchko. So it's only in 2018 that I learned of the existence of this important paper. Another part of the story here is that during a seminar of mine in which I was presenting similar results, Charles Goldie, who is one of the authors of a famous book and former probabilist at the University of Sussex, asked why complete Bernstein functions are needed for evolution equations of semi-Markov processes. And now I can reply, if I am not mistaken, that they are not needed, essentially. So, I mean, it's a nice theory, but you just need the distribution of inter-event times. And so this operator here, where this is a kernel depending on the distribution of inter-arrival times, is not a fractional derivative because you don't have Sonin pairs, etc. It's not a problem. You can still write such an equation. It still has a meaning. So let me illustrate this point with a simple example. I like, maybe instead of writing very general theories, to start from constructive presentation or constructive definition of stochastic processes, and in particular, my interest is in characterizing time-changed Markov chains. So we have a Markov chain in discrete time, and now let us define the time change. And one of the simplest way of defining this time change is in terms of a renewal process. So you have a sequence of independent and identically distributed positive random variables with a probability density function and with the meaning of inter-event times. You can define this random walk here, the Tn. So the Ji's are the inter-arrival, inter-event times. And the Tn's are the renewal epochs, or the times at which events occur and renewal happens. And they are essentially a random walk, a sum of these positive IID random variables. This is the process of the epochs, and this is its inverse. It's the counting process. So this number here is counting the number of events between 0 and t. So this is taking values in integers. Now, of course, we can define the 1 point probability of that particular counting process. And we use this symbol here, capital P of nt, as the probability that there are n events between time 0 and time t. Remember that in this construction, time 0 acts as a renewal point. So 0 is a renewal point. It's not a generic time. Otherwise, the construction of the process would be a little bit more complicated. I mean, just for simplicity, let us assume that time 0 is a renewal point. Okay, now we denote by f bar the complementary cumulative distribution function of the ji's. We just need the one for j1 because they have the same distribution, and this is the probability density function. By quite simple probabilistic considerations, you can derive this nice result in terms of the Laplace transform of the probability of having n events up to time t, and you see that it can be written as the product of the Laplace transform of the complementary cumulative distribution function and the nth power of the complementary of the density. If you're interested, I can give also more details. By the way, this function here is the opposite of the derivative of the complementary cumulative distribution function, and so you also have this relationship between the two Laplace transforms. So if you just want to use the Laplace transform of the density, you can do that. If you just want to use the Laplace transform of the complementary cumulative distribution function, you can do that as well. And now the time change process we are interested in is defined in this way. Instead of considering a deterministic value of n in here, we replace small n with capital N of t, with the counting process. So this will be a random number. And if nt is the Poisson process, which means that the distribution of these ji's is exponential of parameter lambda, or in this presentation, I set lambda equal to 1. Lambda is just a change of scale in time. So if you set it equal to 1, you don't lose in generality. But of course, if you have to discuss realistic systems with these models, the time scale may be important. But let's say for the sake of this presentation, I will set lambda equal to 1 almost always, but not always. And this is only the only case where you have still a Markov process. So this can be proven in various ways, and I believe a proof of such a result can be found, for instance, in a famous book on stochastic processes written by Chinlar. Otherwise, you can even use some results we obtained with Kaizoji and Politi. But I mean, let's say that is an if and only if. And here I just wrote one of the two conditions. If n is the Poisson process, this is still a Markov process. Note that we were starting from a process in discrete time, and with this time change, the process becomes a process in continuous time. If you replace here any other renewal process, this is no longer a Markov process, but it becomes semi-Markov. By semi-Markov, it means that there is a long-range dependence of a random variable, which is the residual lifetime. Or if you prefer, if you consider the age and you couple the age with the original Markov chain, this is still a Markov process. In any case, we will not need a precise definition of semi-Markov processes. It suffices to recall that if nt is not the Poisson process, this m of t is no longer Markov, as you will see also from the evolution equation. Okay, now that we have established what we are interested in, so this time-changed Markov chain, let us consider a simple example, which is a Markov chain of alternating +1s and -1s. So here, if n is equal to 0, you start from +1, then you get -1, +1, -1, and so on. So you have a periodic deterministic Markov chain, which is one of the most boring Markov chains you can imagine. Okay, maybe the one where there is no change of state is more boring than this one, but of course, this is quite boring. But now consider NT be the Poisson process with parameter 1, and this time change here. So you have what I would call a telegraph process in the sense that it has two levels and it alternates within these two levels. But at this time, this is less trivial than before, because you have that you stay in -1 or +1 for a random time. And in this particular case, the random time is exponentially distributed with parameter lambda equal to 1. Okay, now you can have further generalizations of this. For instance, you could have alternating renewal processes. You could consider this as a generic counting process, for instance, I don't know, or a more even more general process like Hawkes processes, whatever you like. But we are considering this simple case where this is the Poisson process. It's a case that was studied by Mark Katz, among other people. And now let us define the probability that at time t, we observe 1 when we started at time 0 with 1. We will consider only this case. Again, if you look in the literature, and especially in the physical literature, usually they deal with this process either when it is starting from -infinity, and then I will tell you what happens if the process is starting in the remote past, or maybe as a mixture of initial conditions equivalently, let's say where you have 1 and -1 in 0. But now, I mean, nothing prevents us to consider this condition that at the beginning the process is equal to 1. And so we are interested in both the probability of finding 1 and the probability of finding -1. Okay, you would say, what about the finite dimensional distributions? Well, why not? But I am not deriving today the finite dimensional distributions. It's a nice exercise to find the finite dimensional distributions for such a process, but I am just interested in these two quantities here. Why is it so? Because especially in applications, when you are sampling, maybe you can find information, statistical information that is sufficient on maybe this 1 point object, maybe on correlations. On 3 and 4 points, you start lacking statistics, even if your measurements are quite low. However, let's say, this was just to prevent a question on finite dimensional distributions. But you're free to ask it. So remember that because of this condition, you have that the probability of finding 1 at time 0 is 1, and the probability of finding -1 times 0 is 0. Very nice. Okay, so by purely probabilistic arguments, now you can find that explicitly the probability of finding 1 at time t. This is given by the sum on even numbers starting from 0 of the probability of finding n events from time 0 to time t. And similarly, the probability of finding -1 is the probability of having a sum on odd numbers on the 1 point probability of the counting process. So the event of finding this situation, this conditional event here, and the event that n is even or n is odd are equivalent somehow. It turns out you can do these sums and you get this nice result here, which, by the way, it fulfills the initial condition for t equal to 0. This is 1, this is 0. And yes, so you can also see what happens when you let t diverge to plus infinity. You get 1/2 here and 1/2 here, if I'm not mistaken, which is exactly what you will find in the physics literature on these processes in physics papers. Yes, so just to get these results, you have to remember that this is the Poisson process. So this has this shape. Then here you are summing these terms for the exponential only on even numbers and only on odd numbers, and then that's why you get the hyperbolic cosine and the hyperbolic sum. Okay, you can either directly differentiate these equations, or if you prefer, you can use Chapman-Kolmogorov equations. In any case, whatever method you use, you get the following system of governing differential equations for these two probabilities. So you have that the time derivative of p1t is given by minus p1t plus p minus 1t, and the time derivative of the probability of minus 1t is the probability of 1t minus the probability of minus 1t. And the initial conditions for this system are 1, 0, probability in 1, 0 equal to 1, and probability in minus 1, 0 equal to 0. If you solve this system, you get these solutions here, and you can also observe that here you are multiplying the vector of p1 and p minus 1 by minus I minus p, where now p here, maybe I should have used another symbol, q and not p, but here p is the transition probability of the original Markov chain. And remember, the original Markov chain was a periodic Markov chain, periodic between two states, so it would be a transition probability matrix which has in the first row 0, 1, and in the second row 1, 0. The identity matrix is 1, 0, 0, 1. Minus I minus p is exactly the matrix that you find here, which is the semigroup generator of the Markov process. Okay, now we have seen what happens if n of t is Poisson, and now what happens if n of t is a generic non-Poissonian renewal counting process. In other words, what happens if, for instance, these ji's follow the Weibull distribution or any other distribution for inter-arrival times? Well, it's not difficult to prove this proposition. Let nt be a generic counting renewal. Let me read it. Let nt be a generic counting renewal process. Let f small j and capital F bar j be the probability density function and the complementary cumulative distribution function of inter-arrival times, respectively. Then you have the following equations for P1t and P minus 1t, where you have on the right-hand side the same situation as before, but on the left-hand side you have this convolutional integral where you have the integral from 0 to t of this kernel phi that multiplies the first derivative of P1 or P minus 1 and then integrated over dt prime with the same initial conditions. And what is this kernel? This kernel is a kernel that is coming from a Laplace transform where you have the Laplace transform of the kernel is the ratio between the Laplace transform of the complementary cumulative distribution function and the Laplace transform of the probability density function. For the Poisson process, you get that the kernel is a delta function, Dirac's delta function. And for instance, if you get a fractional Poisson process, the kernel has this shape. And so in this case, the operator on the left-hand side becomes the Caputo derivative that you have already seen in many cases. But if you have not seen it, you can just replace this into here and call this the Caputo derivative with initial conditions that stay the same. Okay, so in these two cases, and especially in the second case, we are in the situation in which we have, let's say, Kochubey, Luchko, Toaldo, etc., Merschert-like situation, because I think there is an inverse or left inverse for this differential operator, but in general you don't have it, but still you can write the equations that I wrote before. In fact, here the only assumption is that I am dealing with the generic counting renewal process. Okay, maybe in this case we can say and do more. In a famous paper by Begin and Orsinger in 2010, thanks to the fact that I can ask Luisa Begin moving out of my office, I could essentially perform these summations in the case in which this is the counting probability for the fractional Poisson process. And in that particular case, you get these two nice results. Actually, here you can write this one minus t to the beta, etc. This is the two-parameter Mittag Leffler function. Or again, I am not going into the details of the two-parameter Mittag Leffler function here, but just to mention that even in this case, you can write down an explicit analytical solution, as it is often the case when you deal with Mittag Leffler distributed random variables and with the fractional Poisson process. So I do not understand why people still use Pareto distributions when they want to describe power law behavior when beta is smaller than 1, when it is so nice to use the Mittag Leffler distribution and the Mittag Leffler counting process, so the fractional Poisson process, as you have so many analytical results. But that is the word. Okay, so you have seen this simple example. It is general enough to conclude the evolution equations such as the ones that I wrote here in this proposition are appear every time one replaces the deterministic n in a Markov chain with the renewal counting process. Okay, now we can move to continuous time random walks in the second part of the talk. You will recognize in equation 3 the same pattern as before, because we are changing the time in a random walk. Instead of having here deterministic small n, we consider a random sum of random variables. So these yi have the meaning of jumps or steps. They can be positive and negative, or all positive or negative, depending on the application. So maybe in insurance, you would like this sum here, have these yi's being positive, because then you remove it from a steady growth of the capital of the insurance company. In finance applications, these are log returns. So, okay, stylized log returns, then maybe they are even symmetrically distributed, etc., etc. But the only difference here with respect to before is that before I was implicitly assuming, as in the example, that I had a Markov chain with a finite state space. Here I have a Markov chain with a countable but not finite state space. Yeah, because we are moving, and it could be even uncountable if the yi's are not integer numbers. So in any case, we are moving on Z also. Okay, that's nice. This object here is the so-called uncoupled continuous time random walk. If NT is a Poisson process, this is also called a compound Poisson process. If it is a renewal process, it's also called compound renewal process, etc., etc. Again, as before, we focus on the derivation of equations for the 1 points. Here, I should say focus on the derivation. Oh, well, it's fine. On the derivation of the 1 point probability density function. So what's the probability of finding the process close to point x at time t? Here we cannot say exactly equal to x in general. If these yi's are continuous, this is a probability density somehow. And the scaling of this probability density function leads to the solution of the Cauchy problems for the generalized diffusion equations, as we will see soon. Okay, in the paper by Mainardi, myself, Roberto, and Gorenflo, we proved that the evolution equation for the continuous time random walk is of this kind here, equation 4. You see again this operator here, and on the right-hand side, you have the same structure as the system 1, 2. So there is a semi-group generator of the random walk. Okay, now the ingredient for the stochastic solution of differential equation, be it a standard differential equation or a fractional differential equation, is the simulation of a stochastic process. And in this case, the simulation of a continuous time random walk. This is very simple in a sense. It suffices to generate a finite sequence of the ji's. Then you compute their cumulative sum, which gives the epochs here. Then you simulate a finite sequence of the jumps, and their cumulative sum gives the position of the continuous time random walk at the instance where events occur. And then you just plot xn versus tn, and you're done. You have your continuous time random walk. If you are interested in the value at a given time, instead of computing a finite sequence, you can use a while loop, and you stop the simulation when the sum of the ji's is greater than t. And then the normalized histogram of xt approximates the probability density function that I have mentioned before. Okay, before delving into the theory, this is an example in R. So I select small t equal to 10 is the time at which we plot the solution. This is the number of iterations of the process. This is the vector of positions at time t. This is the counting process. And so, for instance, for I in 1 to the number of iterations, you sample, for instance, 30 values of j's and jumps. So, for instance, here I am using the Weibel distribution for the waiting times, but here you can insert your favorite distribution. And again, your favorite distribution for the jumps. You set the initial conditions for the epochs and for the positions. They can also, I mean, I'm starting the processes in 0 at time 0, but you could start at time 0 wherever you like. Then you compute the cumulative sum of the inter-arrival event times and the cumulative sum of the jumps. Then you add the initial conditions. Then you stop your simulation at time 10. So this is a way of avoiding the while loop, but it's equivalent to a while loop. And then you put the values of nt and xt into a vector. Then a single realization of the process where the point 0, 0 is probably not represented here, or maybe it is represented as this shape. I am highlighting the values of the xn's with these black dots and then black red dots here. I can even make it a bit larger. Okay, and yes, so this is a nice single realization of the process, but you are interested maybe also in the approximation of the probability density. And let's see what we get. Sorry. Yeah, here we are. So this is for Weibel distributed waiting times. This is the position at time equal to 10. And it's a histogram over 100,000 simulations. And you see that there is this peak in 0, because this is related, as you will see soon, to the degenerate behavior of this probability density when you are in 0. So in other words, the probability density function has a delta in 0, and then it has a continuous part outside 0, which is represented by this histogram. Okay. So maybe a good point to see if there are questions. No, I don't see anything in the chat. So I will go on then with the presentation. Okay, so you have seen what I have summarized in this transparency. Now, why do we have this peak in the origin? Let us see. So the one-point cumulative distribution function, you can derive it by elementary probabilistic considerations. In other words, say this is the cumulative distribution function, yes? So the probability that xt is smaller or equal than x. It may happen that you do not overcome x with 0 jumps, 1 jump, 2 jumps, etc. So you have this n-fold convolution, which would give you x, because this is a sum, yes? So if you have a sum here with a finite n, you would have this as the probability of xn being smaller or equal than x. But then you may have 0, 1, 2, 3, up to infinity jumps. So you have to sum also the probability of having n jumps up to time t over n, all the possible values of n. So here you have exhaustive and mutually exclusive events. And so you are using the third axiom of Kolmogorov to get phi. The corresponding probability density you derive this is this one, where you have here the n-fold convolution of the probability density for the single jump. So these formulas are nice because we have assumed independence between jumps and waiting times, and then everything else is also independent. So you have these nice relations. Otherwise, things you can still write things, but they become more complicated. Good. So this is what we were looking for, and if you consider Fourier Laplace transform of that formula, you get to this nice equation 7, which is the famous Montreal-Weiss equation for continuous time random walks. You see here you have a geometric series where you have this product here, which has values smaller than 1, so you can sum them. This is not depending on n, it goes out, and you get this equation 7. If you rewrite this and you come back in space and time by inverting Laplace and Fourier transform, you get to equation 8. You can call it a semi-Markov renewal equation that you can also write for other Markov chains. And here you understand why you have the peak in 0, because there is a finite probability which is given by the cumulative distribution function that the particle that is diffusing lingers in 0 up to time t. Otherwise, it moves, and you have this equation 8. Okay, so you can see special cases. For instance, I don't know if you have ever done this, but you can consider the case in which you have the Poisson process of parameter lambda. This time lambda is no longer equal to 1, and the jumps have a normal distribution with which is symmetric with mean 0 and variance sigma square. And then the explicit form of the probability density of finding the continuous time random walk in x at time t is given by this infinite sum here. You can get out of this formula a central limit theorem. When you fix t, you have a random variable. You can consider therefore scaling limits. Sorry, one of these scaling limits is when you send the activity of the Poisson process to infinity, and you consider smaller and smaller jumps. But the limit of the product lambda sigma square converges to 1 or is equal to 1 also all over your sequence of random processes. So you have a sequence, not a random process, of random variables here because we fixed it. So you can consider, to get the result in the limit, the characteristic function of xt, and which is given by this formula. It's just the Fourier transform of the previous one. And here I am rearranging the terms. And up to equation 9, because I am summing this. You see that you have this exponential here, and then you have this exponential here, and you get this equation. I hope maybe I made there is a misprint here, in my opinion, because there should be another parenthesis here. But apart from that, now if you consider the scaling limit, this object here becomes the exponential of minus t to absolute value of k squared divided by 2, which is, not surprisingly, the solution, the green function, of the standard diffusion equation. In other words, if you are simulating the continuous time random walk with the Poisson process for the change of time and with these jumps here, and you start making lambda larger and larger and sigma smaller and smaller, you get a nice stochastic approximation of equation 11, which is the solution, fundamental solution or green function for the standard diffusion equation. I am not doing this using the program, but you can, based on the program that I am sharing with the organizers, if you want to modify it, or you can write your own, of course, because it's very easy. You can check that you get closer and closer to that stochastic that function when you are considering the histogram. Yes, so here this transparency is just to show that if you are solving this equation, this initial condition, you get exactly equation 10, which is the limit of the stochastic of the continuous time random walk. Now, suppose that instead of having the Poisson process for the renewal counting process, you have a Mittag Leffler counting process, so the fractional Poisson process. This is the probability of finding n events up to time t for the fractional Poisson process. And you can very easily simulate also a fractional Poisson process, because Mittag Leffler distributed intervals are very easy to simulate. And suppose then for the jumps, instead of using the normal distribution, you assume that they are distributed according to an alpha stable distribution with index alpha between 0 and 2. The index beta is between 0 and 1, and alpha between 0 and 2. So if we use these two assumptions, we can compute the characteristic function for the continuous time random walk. It is given by this equation 15, which is now correct, and which becomes the previous one when beta is equal to 1 and alpha is equal to 2. Now, you consider a different scaling you multiply the jumps by a parameter h and the waiting times by a parameter r. You let both h and r converge to 0, and however, with the limit for h, r going to 0 of this ratio here being equal to 1. This one gives, there is this proposition, so the probability, the rescaled probability of the continuous time random walk weakly converges to the green function of the space-time fractional diffusion equation. So if you use this theorem, you're able to use the simulation of the continuous time random walk with Mittag Leffler interarrival times and alpha stable jumps, symmetric alpha stable jumps, to solve, to find the solution of the space fractional time-space fractional diffusion equation. So, by the way, you do essentially the same thing as before by getting a nice extension of the central limit theorem. In this case, we are working on the characteristic function, so we need Levy continuity theorem to complete this result, but it is there, so why not? And this limiting function here is such that it solves the following problem, where this is the Caputo derivative and this is the fractional Laplacian in one dimension, with initial condition always given by delta of x. This is also showing that if you take this equation and you take the Fourier Laplace transform, actually just the Fourier transform here, you don't need the Laplace transform, you get really this equation here. Equation 17 is the nice eigenvalue equation for the Caputo derivative, and the unique solution of the problem is the Mittag Leffler function computed in minus t to the beta absolute value of k of kappa, sorry, to the alpha. Okay, some final remarks. So I focused, and as in the paper in 2008, on the central limit theorem for random variables, because this is what we usually need. So we usually fix a time and present the results of the simulation as a function of x, and also the function that we want to compute, we will plot as a function of x. But the behavior, if you like, it's, I mean, we have even stronger forms, well, stronger. I mean, we also have convergence of the continuous time random walk as Cadillac process in some Skorow topology to the limiting process, and the limiting process would be governed by that fractional space-time fractional diffusion equation. So the one-point probability distribution of the limiting process will have that equation as governing equation, and the limit will be an alpha stable process, time changed with inverse beta stable subordinator. Okay, so if you're interested in this behavior and in functional convergence, apart reading the books by Billingsley, Jacot and Chiryaev, etc., you can also refer to the papers by Becker-Kern, or Kern, Merschert and Scheffler. And, well, sorry. Also, the paper I presented is from 2008. I noticed this week that Sapienza and Uchaikin had a related idea in 2003, and they published it in Sibirski Journal Vychислitelnoi Matematiki, which is, everything is clear. It's a Siberian Journal of Mathematics. This means computational. I learned this from a paper by Vassily Kolokoltsov. Since 2008, there have been a lot of developments, and on the stochastic solution of non-homogeneous equation, I would like to mention a nice poster by Ivan Biocic, Daniel Cedegno-Giron, and Bruno Toaldo, that was presented at the 4th Italian meeting on probability and mathematical statistics held in Rome very recently. If you have not been at this very interesting conference, you can refer to a paper by Jum and Kobayashi, and the paper from which I learned of the paper by Sayenko and Uchaikin, by Kolokoltsov, Lin, and Mijatovic, Monte Carlo estimation of the solution of fractional partial differential equations. So these are recent papers, so you will be able to find what has been, again, I believe, I mean, paper 2 does not quote us, so I could find the paper by Sayenko Uchaikin only this week. Otherwise, I would have known earlier. And then these are the references. The paper by Mainardi, Goren, Floraberto, and Scalas that I mentioned before for the Cauchy-like equations of Cauchy before Cauchy, and then this paper with Fulger, Germano, and Scalas, which is the one that I have discussed at length in the second part of the talk. And then to see an application of what we have done, there is this paper by Georgiou, Kish, and Scalas, a solvable non-Markovian dynamic network. It's application to mathematical epidemiology, among other things. And if you want to know more, you can contact me at this email address. And I would like to thank you for your kind attention. And once more, thanks to the organizers for their kind invitation. I hope I took a little bit more time than I thought, as usual, but still we are not. We are still in time.
Yeah, we are pretty much in time. So thank you very much for the nice talk. For the questions, I request the audience to kindly raise their hand, and I'll call out your name as they appear on my screen. I see where Professor Kolokso has a question. Please go on.
Well, thank you, Enrico, for a very nice talk. And first of all, I really like to apologize. You said you didn't know about the paper of Sayenko Uchaikin. And in the same way, I didn't know about your paper. And therefore, in our paper with Mijatovic, I didn't cite it, which was really a mistake. And it will be corrected in the future. But mostly important, really, I'd like to make a point about my paper of last year,
yes,
which I really started a new direction on the rates of convergence. So I was really surprised that for 50 years from this continuous time random walk and all this theorem that this converges to this, there was nothing done about the rates of convergence. So in the previous year, I published a paper, Rates of Convergence, where the first time really, I'm sorry to be so proud, but it's only 50 years.
No, you're right, yes.
And it really makes, your results, it put it much more sound basis. It's not just convergence, okay? So in some sense, convergence is good, but from practical side, it does not tell us anything, yeah? But in my paper, I really give you rates of convergence and precisely, in particular, your setting. So you can really say, what is the difference between what you calculated with your continuous time random walk and what is really the limit?
Yes.
So maybe you will find it of interest to look at it.
I noticed that you already
mathematics, rates of convergence of something.
Yes, I noticed that in your paper.
Can you hear?
Yes, as I can hear you. Can you hear me? Hello?
Yeah, I can hear you.
Okay, so I noticed that in the paper by Vassily Kolokoltsov with Mijatovic, there was already a nice discussion of rate of convergences based on Berry-Issin estimate. And Vassily Kolokoltsov is right about, I think we lost connection with him, or?
Yes, I lost connection, yes.
Yeah.
Now I'm back.
Yes. So you're right that rates of convergence have been neglected somehow, and indeed, I've been surprised to discover, for instance, that for the Ehrenfest-Ern model, there is a paper of the previous decade, maybe 2016-17, by Diaconis and Salov-Coste about rate of convergence. And next week at the European Mathematics Colloquium in Seville, I will be presenting some results that we got with Nikos Georgiou on rate of convergences of Markov chains, time change Markov chains of this kind, when we have some general results on the time change, let's say, but we have also some specific and stronger results when n of t is the fractional Poisson process. This is a paper that we published a couple of years ago somehow. So it's probably, I will send it to you. So.
Yes, please do. Yes, and please have a look on my paper last year about this.
Yes,
Nice
I think I've seen already your paper of last year. Yes, and I will share it also with Nikos, and we will go on with that. Thank you very much.
Okay.
Are there more questions or comments? I don't see any raised hands, so I believe this is a good point to stop here. Thank you very much, Professor Scalas, for the nice talk. It was very nice having you.
Thank you very much.